In many statistical applications, we are not just interested in computing probabilities. Instead, we often start with a probability and want to determine the corresponding cutoff value. This cutoff is called a quantile or percentile. For example, we might want to know the value below which 95% of observations fall. In this section, we will learn what quantiles are, how they relate to the cumulative distribution function, and how to compute them for normal distributions using a simple step-by-step process. By the end, you should feel comfortable moving from a probability to the associated value of the random variable. Let's begin with the basic idea of a quantile. A quantile is the value x such that the probability that the random variable is less than or equal to x equals some specified probability we will denote as p. In symbols, we write this as probability of x less than some value of x equal to p. You can think of this as working backward from probability to value. Instead of asking, what is the probability of being below this number? We ask, what number corresponds to this probability? The quantile function, often written as f inverse of p, is the inverse of the cumulative distribution function. For normal distributions, this inverse does not have a simple algebraic formula, so we typically rely on software or statistical tables to find it. It is helpful to contrast the cumulative distribution function, or CDF, with the quantile function. The CDF, written capital F of x, takes a value x and it returns the probability that the random variable is less than or equal to that value. In other words, it accumulates probability from the left. The quantile function reverses this process. It takes a probability p as input and returns the corresponding cutoff value x. A familiar example is the 0.5 quantile, which is simply the median of the distribution. Because the normal distribution's CDF does not have a simple inverse formula, we almost always use statistical software, calculators, or tables to obtain normal quantiles in practice. In many statistical settings, we use special notation for standard normal quantiles. You will often see expressions like p equals the probability of z, greater than some value z subscript p. This means that z subscript p is the value on the standard normal scale that leaves probability p in the right tail. For example, the value z subscript 0.05 is the cutoff where 5% of the area lies to the right. Visually, this corresponds to shading the upper tail of the standard normal curve. Understanding this notation is important because these special z values appear frequently in hypothesis testing and confidence interval formulas in later videos. Let's now outline the general procedure for finding quantiles for a normal distribution. Step 1 is to clearly specify the probability you are targeting and determine whether it is a lower tail, upper tail, or two-sided situation. Step 2 is to find the corresponding z-score from the standard normal distribution using software or tables. Step 3 is to transform that z-score back to the original scale of your variable using the formula x equal to mu plus z times sigma, where mu is the mean and sigma is the standard deviation. Following these 3 steps consistently will help you avoid many common mistakes when working with normal quantiles. Now let's look at an example from therapeutic drug monitoring. Suppose drug concentrations after dosing follow a normal distribution with mean 50 and standard deviation 10. Physicians want to determine the upper control limit corresponding to the 97.5 percentile. Because 97.5% is to the left, that leaves 2.5% in the right tail. Therefore, we look for the standard normal value z subscript 0.025. Using statistical software or the jump calculator shown in the image, we find that this z value is approximately 1.96. This step converts the probability question into a standard normal cutoff. In the final step, we transform the z-score back to the original measurement scale. Using the formula, we substitute mu equal to 50, sigma equal to 10, and z equal to 1.96. This gives x equal to 69.6. The interpretation is that only about 2.5% of patients are expected to have drug concentrations above 69.6 nanograms per milliliter. Therefore, values exceeding this threshold may be considered unusually high and could trigger clinical review. This example illustrates how quantiles translate probability statements into meaningful real-world cutoffs.